Alloying elements are included in the base metal lattice, the general arrangement of individual atoms, in various ways, depending upon the relative sizes of the atoms. Smaller atoms, such as carbon, nitrogen, and hydrogen, tend to occupy sites between the atoms that form the lattice structure of the base metal. This is known as interstitial alloying, and is shown in 2 dimensions on your screen at this time. For example, small amounts of carbon can occupy the interstitial sites between the iron atoms in steel. Alloying elements with atoms close to the size of those of the base metal tend to occupy substitutional sites. That is, they replace one of the base metal atoms in the lattice structure. This is called substitutional alloying, and is shown on your screen at this time. Examples of this are both copper in nickel and nickel in copper. Like the presence of grain boundaries, the addition of alloying elements produces irregularities in the lattice structure. As can be seen in both items displayed on your screen, the presence of alloying elements exerts varying degrees of atomic attraction and repulsion to result in a lattice arrangement which is somewhat distorted or strained. This tends to increase the internal energy of the metal and can result in improved mechanical property. Nearly all engineering metals are alloys consisting of one major element and variable amounts of one or more additional elements. Alloys usually consist of many randomly oriented grains, with each grain arranged in a specific way and containing one or more of the characteristic phases that exist for the alloy. If more than one phase is present, each will have its own characteristic crystalline structure. The overall arrangement of grains, grain boundaries, and phases present in a metallic alloy is called its microstructure. The microstructure is primarily responsible for the properties of the alloy. This microstructure is affected by the composition or alloy content, and by other factors, such as forming and heat treating operations. The microstructure is greatly affected by the welding operation, which, in turn, influences the properties of the alloy. While all metals exhibit various microstructures, this discussion will deal exclusively with the microstructural changes that occur in plain carbon steel, which is an alloy consisting of iron in combination with carbon. Other alloying elements may be included as well, but their effects on the microstructure will not be as significant as those of carbon. To introduce this topic, it is important to realize that iron in steels undergo changes in their crystallographic arrangement as a result of temperature changes. That is, as iron-carbon alloys are heated or cooled, phase changes occur. The occurrence of this phenomenon allows us to change the mechanical properties of a specific alloy through the application of various heat treatments. To understand the changes that occur, the metallurgist uses a chart, or phase diagram, which graphically displays the ranges of various microstructural components for the iron-carbon system. Referred to as the iron-carbon phase diagram, it is shown on your screen at this time. This diagram describes the nature of the phases present in iron-carbon alloys under near equilibrium conditions, such as very slow heating and cooling. It should be noted that many of these microstructural constituents have multiple names which are used interchangeably. For example, pure iron at room temperature is referred to as alpha iron or ferrite. The iron carbide which is present at room temperature is called cementite or Fe3C. The face-centered cubic structure which occurs at intermediate temperatures is referred to as either austenite or gamma iron. Looking at the diagram, notice that the vertical axis describes the temperature changes, while the horizontal axis indicates the amount of carbon present. Consequently, for a given carbon content, a vertical line can be drawn through that horizontal axis intersect. Moving vertically up that line, it can be determined what microstructures will exist at various temperatures. As shown in the notation below the horizontal axis, steels are considered to include those iron-carbon alloys having from 0.008% to 2% carbon. Within this range, the steels are further divided into hypoeutectoid, eutectoid, and hypereutectoid types, with the eutectoid point, 0.8% carbon, being the dividing line. Hypoeutectoid steels are those alloys with less than 0.8% carbon, which exist at room temperature as combinations of pearlite and ferrite, as opposed to hypereutectoid types, which contain more than 0.8% carbon, and exist as combinations of pearlite and cementite. The room temperature equilibrium microstructure for a eutectoid steel, exactly 0.8% carbon, is pure pearlite. Pearlite is a layered mixture of cementite and ferrite. The technique of polishing and using an acid etch reveals the microstructures, which are shown in the displays on your screen. The display on the top portion of your screen shows the typical microstructure of commercially pure iron, or ferrite, with almost no carbon content. The display on the bottom portion of your screen shows the typical appearance of pearlite when polished, etched with acid, and viewed under a high-power microscope, 1500 power. The light areas are ferrite, and the dark areas are cementite. One of the important transformations which occurs in steel is the transformation from the various room temperature constituents, ferrite, pearlite, cementite, and combinations of these, to austenite, which is the face-centered cubic structure of iron and carbon. Upon heating, this transformation will begin to occur at 1,333 degrees Fahrenheit. The horizontal line representing this transformation temperature is referred to as the A1. Except at a carbon content of 0.8%, the eutectoid percentage, this transformation will occur over a range of temperatures, with complete transformation occurring only when the temperature is raised above the sloping line designated as the A3. In pure iron, the transformation is complete at 1,670 degrees Fahrenheit, while a eutectoid steel will undergo this complete transformation at 1,333 degrees Fahrenheit. Upon very slow cooling, these same changes will occur in reverse. It is the existence of this transformation that permits us to harden or soften steels through the use of various heat treatments. When a steel has been heated into the austenitic range and then allowed to cool slowly through this transformation range, the resulting microstructure will contain pearlite. This structure can only occur when sufficient time is allowed for the atoms to diffuse into that arrangement. Diffusion is simply the migration of the atoms within the solid metal structure. The higher the temperature, the more mobile the atoms become in the lattice structure. When cooling from austenite occurs slowly enough, pearlite will form. Steels that are heat-treated to produce pearlite are generally very soft and ductile. When the cooling from the austenitic range occurs more rapidly, there are significant changes in this transformation for a given steel alloy. First, the transformation will occur at a lower temperature. Secondly, the resulting microstructure is drastically changed, and the hardness and tensile strength of the steel increase significantly, with a corresponding decrease in ductility. At faster cooling rates, the principal microstructures produced include fine pearlite, bainite, and martensite. With a slight increase in cooling rate, the transformation temperature is depressed somewhat, producing a finer pearlitic structure, with the lamellae more closely spaced. This structure is slightly harder than the coarse pearlite and has somewhat lower ductility. At still faster cooling rates and lower transformation temperatures, pearlite no longer forms. Instead, bainite is formed, and this structure has a feathery arrangement of fine carbide needles in a ferrite matrix. Bainite has significantly higher strength and hardness and lower ductility, and is very difficult to see under the microscope. Upon very rapid cooling or quenching, insufficient time is available for diffusion to take place. Consequently, some of the carbon becomes trapped in the lattice. If the cooling rate is fast enough and the amount of carbon present is high enough, martensite will be formed. The formation of martensite is a diffusionless process. The cooling rate is so rapid, the atoms do not have time to move around. The transformation from austenite to martensite results from a shear type or mechanical action. The resulting crystalline structure is referred to as body-centered tetragonal, which is a distortion of a body-centered cubic structure into a rectangular one. Due to the presence of this distorted lattice arrangement, the martensitic structure exhibits a higher internal energy or strain, which results in extremely high hardness and tensile strength. However, martensite has a characteristically low ductility and toughness. The display on your screen shows the appearance of martensite at a high magnification, 500 power. To improve the ductility and toughness without significantly decreasing the hardness and tensile strength of the martensite, a process referred to as tempering is employed. This heat treatment consists of reheating the quenched martensitic structure to some temperature below the lower transformation temperature, 1,333 degrees Fahrenheit. This permits the as-quenched, unstable martensite to change to tempered martensite by allowing the carbon to precipitate in the form of tiny carbide particles. The desired strength and ductility can be controlled by choosing the proper tempering times and temperatures. Higher tempering temperatures result in softer and more ductile properties. Quenching and tempering heat treatment is frequently used to enhance the properties of machinery steels, since it develops high yield and tensile strengths, high yield strength, tensile strength ratios, and improved notch toughness as compared to the rolled, annealed, or normalized properties. An example of the effects of various tempering temperatures for a particular steel alloy is illustrated in the display on your screen. To aid in the determination of what microstructural constituents will result from rapid cooling rates, the metallurgist uses another diagram which is referred to as a TTT diagram, or time, temperature, transformation diagram. These are also called isothermal transformation diagrams, or IT. As the name implies, it describes the microstructural products which can occur after specific times at a particular temperature for a particular steel composition. A similar diagram, the CCT, or Continuous Cooling Transformation Diagram, shows the changes that occur during continuous cooling from the austenitic range. These two types of diagrams agree quite well. The display on your screen depicts the continuous cooling transformation characteristics of type 8630 steel. This diagram shows the microstructural products as a function of both temperature and time. Various cooling rates are shown to illustrate how the diagram is used. The resulting transformation products depend on the regions through which the cooling curves pass, and the amount of time it takes for the cooling curves to pass through those regions. As an example, curve A only passes through the austenite to martensite region, so the resulting microstructure is 100% martensite. The slower cooling rate, characterized by curve D, shows that the resulting microstructural components will be primarily ferrite, with only minor amounts of bainite and martensite. Since martensite can only transform from austenite, any austenite which transforms to ferrite or bainite cannot transform to martensite. Since welding can result in significant changes in both the temperature of the metal as well as the rate of cooling from that elevated temperature, it is important to understand what metallurgical changes can result from the welding operation. The display on your screen illustrates the relationship between the peak temperatures exhibited in various regions of the weld zone and the iron-iron carbide equilibrium diagram. As can be seen, depending on the location of a point within or adjacent to the weld, there can be various metallurgical structures produced. Within the weld, the region of highest temperatures, the metal can cool from the liquid through the various phase regions noted earlier. Adjacent to the weld, in the heat-affected zone, or HAZ, no melting occurs, but extremely high temperatures can be reached. The HAZ is that region of the base metal adjacent to the weld metal which has been raised to temperatures from just below the transformation temperature to just below the melting point of the steel. Cooling rates in this heat-affected zone are among the most rapid because of a phenomenon known as contact quenching. Changes in the welding conditions can have a very significant effect on the formation of the various phases, because the welding conditions have a significant effect on the resulting cooling rate for the weld. Some of the welding conditions which could produce changes include the amount of heat input, use of preheat, carbon equivalent of the base metal, and the base metal thickness. As the heat input increases, the cooling rate decreases. The use of smaller diameter welding electrodes, lower welding currents, and faster travel speeds will all tend to decrease the heat input and therefore increase the cooling rate. For any arc welding process, the heat input can be calculated. It is dependent only on the apparent welding current, arc voltage, and travel speed, as measured along the longitudinal axis of the weld joint. The formula for welding heat input is shown on your screen. Heat input equals welding current times welding voltage, divided by welding travel speed, or inches per minute, times 60. For this formula, heat input is expressed in terms of joules per inch and travel speed in inches per minute. Joules can also be expressed as watt seconds. Therefore, the 60 occurring above the line in the formula converts the minutes in the travel speed into seconds. Welding personnel may be asked to monitor the welding heat input to control the resulting microstructural properties occurring in the heat-affected zone. Another item which has a significant effect on the resulting microstructure of the heat-affected zone is the use of preheat. In general, the use of preheat will tend to reduce the cooling rate in the weld and HAZ, resulting in improved ductility. When no preheat is used, the heat-affected zone is relatively narrow and exhibits its highest hardness. In some cases, depending on alloy content, Martensite may be formed. However, when preheat is included, the heat-affected zone is wider and the resulting hardness is significantly lower due to the slower cooling rate, which allows for the formation of ferrite, pearlite, and possibly bainite instead of martensite. Therefore, welding personnel may be asked to monitor the preheat required for a particular welding operation. This requirement is primarily concerned with slowing down the cooling rate in the heat-affected zone to produce microstructures having desirable properties. Another important factor for the welding of a steel is its carbon equivalent. Since carbon has the most pronounced effect on the hardenability, the ease with which a metal hardens upon cooling from an austenitic temperature, or its ability to form martensite, of the steel, we are most concerned with how much of it is present in a particular alloy. The higher the carbon content, the more hardenable the steel. Other alloy elements will also promote hardenability to various degrees. An equivalent carbon content is therefore an empirical expression which is used to determine what the combined effects of various alloying elements are on the hardenability of that steel. An example of a typical carbon equivalent content, or CE, is shown on your screen. This formula is intended for carbon and alloy steels containing not more than 0.5% carbon, 1.5% manganese, 3.5% nickel, 1% chromium, 1% copper, and 0.5% molybdenum.